a physical system. So in the last few classes, last class, we actually saw how to model, how you can use differential equation model and try to model different systems such as a mechanical system or an electrical system. And we also saw how you would model a thermal system as well. So today we'll continue a discussion on that, and then we'll move on to a little different topic. So in continuation to our previous class, so today we'll talk about a liquid level system. So in a liquid level system, so let us say that the fluid pressure, so this is basically a liquid level system. So where you have a tank and there is a inflow of liquid and there is a outflow of the liquid. Okay, so and now
excuse me, ma'am.
Yes.
Ma'am, the temperature one was left a little bit in the last class.
Sorry?
The temperature one, temperature model, ma'am, it was left little bit in last class. You said you'll continue today.
Okay, the thermal system you are talking about?
Yes, that thermal system.
Okay, just hold on a second.
Yes, ma'am.
Okay, so in the thermal system, yeah, so we were actually talking about, yeah, this one I think I have covered. So till this point I think I have covered, fine. So what was left out was that, so this was the equation for the differential equation model when we were assuming that the thermal system is nearly perfect thermal system. Nearly perfect thermal system means that it is not having any kind of loss, or the insulation is perfect, then the rate at the temperature of the mixing is perfect. So we were sort of considering idealized conditions. Okay, so now, so this is the equation when you have an ideal sort of condition, then you can represent the thermal system using this kind of an equation where R and C, these were like thermal resistance, thermal capacitance, and the change of temperature with respect to the change in the overall heat content. Now, if you have, let's say, some disturbances. So disturbances as in, let us say that now the inflowing temperature, the liquid which is flowing inside, this cold liquid, the temperature of that cold liquid, it changes by so now let us say the temperature, or wait. So now let's say that the temperature of the inflowing liquid that is changing by an amount of, let's say, theta I. Okay, so this theta I, so this will be considered as the disturbance signal, because we don't want the temperature of the inflowing liquid to change. So this is a disturbance signal. So now we will see what is the effect of the disturbance signal and how our model will change accordingly. Okay, so because the inflowing temperature, the temperature of the inflowing liquid is changing, so that means there will be some extra amount of heat which will be the change of heat. There will be an extra change in the amount of heat because of this delta theta I change. So then you can write that the overall heat content. So the equation of the overall heat content, which was delta H. So then with delta H, there will be another factor. So this factor will come in, delta theta by del R. That will be equal to. So previously our equation was delta H is equals to delta theta by R plus C d delta theta by dt. Okay, so now because since your the input fluid which was flowing, the temperature of that is changing, so there will be a contribution of this temperature change on that overall heat. So that will come on the left hand side, and then the right hand side will remain the same. So it will be d delta theta by dt. Okay, so now if you write this equation, then it will be RC d of delta theta by dt plus delta theta equals to, you will have delta theta I plus R into delta H. So depending on what all are the input parameters in your system, whether there is some external noise or some external disturbance, all of those factors should come into consideration while you are trying to model the system. Similarly, if you see that let us say that the tank insulation is not perfect. So tank insulation is not perfect means that there is some heat flow which is happening through the tank walls, and it is some heat loss is happening from the tank wall to the ambient atmosphere. So then because of that, let us say that because of that the liquid temperature also changes by, let's say, so now let's write that the tank insulation is imperfect. So if the tank insulation is not perfect, so that means the liquid as the liquid temperature rises by an amount of delta theta, there will be some heat flow through the tank walls to the external, to the ambient environment, you can say. Okay, so because of that, there will be a change in the heat flow. So let's say that is denoted by delta theta by some RT. So let's say RT is the thermal resistance of the tank walls. So because of this heat loss, again you need to change the, you need to incorporate this change in heat in the differential equation model of your system. So now then your overall equation will become, you have delta H, then you have delta theta I by R, then you will have delta theta by R. This heat will come here, and then you will have C d delta theta by dt. So in this way, you can see that whatever factors are there which are influencing the input-output relationship of the system, every factor, whether that is a desired change or an undesired change, all of those factors can be and should be considered while modeling a system. Because all of those factors need to be considered, because obviously you would want your model to be an accurate model. You won't want that the overall input-output relation that actually you are getting, and from your model there should not be a large error between those two. So you have to consider all the different parameters, the disturbance signal, the actual input that you are providing, any kind of losses, all these things should be taken into consideration while you are making the differential equation model of the system. So similarly, if you look into a liquid level system, so this liquid level system is basically you have a tank and there is an inflow of liquid and there is an outflow of the liquid, and depending on the rate of fluid flow and the total head or the level of the liquid in or the level of the fluid in the tank, that is maintained or that will change depending on the rate of flow of your fluid. So if you write the fluid pressure, then you can write that in terms of this head. So P equals to rho GH, and this head flow rate, that for a laminar kind of a flow, head flow rate, if H is the head, that is equals to R into Q, and R here is defined as the hydraulic, because we are dealing with liquid level system. So R here will be the hydraulic resistance. Now if you have a turbulent kind of a flow, in case of a turbulent flow, you will have to write the small incremental change in this head flow rate. So delta H will be equals to R into delta Q. So depending on these, the rate of fluid which is stored in the tank, that will depend on how the rate of this head is changing. So we can say that the rate of fluid storage in the tank, that will be equals to some constant A into dH by dt. Fine. Now let us consider a system like this, where the input flow rate of the tank is given by this factor. Let's say it is given by Qi. So let us say this is, let me not write it in this way. Let me write it, this is Qi plus you have delta Qi. Similarly, let me write the output as Q0 plus delta Q0. Fine. And this is H0 plus delta H. Right. So then if you have this, let's say the liquid flow rate into the tank that is given by Qi, the output flow rate is Q0, and at the steady state the head of the tank is given by H0. Okay, so if that is the case, then the so that means if the head is kept constant, so that means the rate of inflow of the liquid and the rate of outflow of the liquid would be same. So Qi will be equals to Q0 if H0 is maintained constant. Okay, so now let us say that there is a rise or there is an increase in the rate of inflow of the liquid. So now the value of Qi has changed to Qi plus delta Qi. So because of this change in the liquid inflow rate, so what will happen? So that means there will be a change in the overall head of the liquid level in the tank, and also there will be correspondingly subsequently there will be a change in the value of Q0, which we are measuring at the output of which is the outflow rate of the liquid. So then you can write that the difference in that Q0, the change in the outflow fluid rate or outflowing liquid rate, that will be given by the delta H. So delta Q0 will be given by delta H by R. Okay, so now the rate of the liquid storage in the tank, that will be the rate of the liquid storage in the tank, or the rate of change of liquid storage in the tank, that will be equals to the rate of inflowing liquid minus the rate of the outflowing liquid. So input minus output will give rise to the overall change, or what is the head of the liquid level inside the tank. So if you write this equation, then the inflow rate of the liquid will be C dH dt, and the or rather the rate of liquid storage that we have defined here is C dH dt, and rate of inflowing liquid is Qi or delta Qi, you can write over here, and the rate of outflowing liquid is given by, the change is given by delta H by R. So now if you substitute everything, then you will get the equation R C d delta H by dt plus delta H will be equals to R into delta Qi. So here also you can see that you can model this liquid level system in terms of a first order differential equation. So now we'll see whether how this liquid level system or this thermal system are analogous to electrical systems. We have seen that the analogy between a mechanical system and an electrical system, right? So similar kind of analogy exists for thermal and inter-domain electrical and thermal, or electrical and liquid level. So how that thing is happening is that, so if you consider a thermal system, so this heat conduction will be, you can consider that, so if you have a conductor like this, and let us say the two ends are maintained at two different temperatures, T1 and T2, and because let's say T1 is at a higher temperature and T2 is at a lower temperature, so that means there is a gradient of temperature, so that means heat will flow from this higher temperature end towards the lower temperature end, and it will be governed by this, let's say T1 minus T2 by the thermal resistance of the conductor. Similarly, if you consider this as a resistor, so then if there is a potential difference V1 and V2, so that means there will be a current flow which will be dependent on the potential difference between the two ends. So from these two figures you can say that if you compare, so that means this voltage is almost, you can say that voltage is analogous to temperature, and the current is analogous to the heat flow rate. Okay, so then you can say that, so if you write the, if you see the make a chart and see what what all parameters are analogous to corresponding parameters in electrical system. So you can see that the charge will be analogous to the total heat for a thermal system, and for a liquid level system it will be the total liquid, the liquid level. And then if the rate of change of heat, the rate of change of charge is equals to current. Similarly, the rate of change of heat will be the heat flow rate, that will be equals to current. Similarly, for a liquid level system, the rate of flow of liquid, that will be equivalent to the current, and voltage will be equivalent to temperature over here, and that will be equivalent to, in case of a liquid level system, the voltage will be equivalent to the overall head, because if there is a head difference between, let us say that if you have two tanks and one has a higher level of, or a higher head of H1, and the second tank has a lower head of H2, so that means because of that head difference there will be a liquid flow between the two tanks. So then you can say that the voltage is actually analogous to the head of the in a liquid level system. Similarly, the resistance will be, in case of a thermal system, it will be thermal resistance. In case of a liquid level system, it will be hydraulic resistance. Similarly, capacitance, thermal capacitance, and hydraulic capacitance. So these are some of the examples of like different kinds of physical systems and how we can actually model those systems, and we have tried to see how these systems are analogous to an electrical system. So now we'll move on to some more examples of this modeling. So if you remember from the, I think from the first or the second class, we had said that there are different steps while modeling a system. There are various steps which we need to follow. So the first step was we need to define what is the purpose of the model. So this was the first step. Then we need to define the boundaries. Boundaries means we need to define what is the environment in which the total system is functioning. Then we have to postulate a structure. Structure as in, we have to assume what all are, so we have to make sure like what all parameters are affecting the system. Then we have to select the variables of interest. Variables of interest means then we need to know what is the input to the system. We need to know what is the output of the system, these things. And then once we have found out what all are the variables of interest, then we'll move on to the mathematical modeling, and we'll apply all the relevant physical or electrical laws whichever are applicable to your concerned system. And after applying those physical laws, then we'll finally come to the final mathematical model. So now let's take example of the cruise control of a car. So cruise control means it refers to the control of the velocity of a car which is moving on a road. So the moment so that means here when the car is moving, so you can understand that the input, or so let's go, okay, so then the input to the system, if the car is my system, then the input to the car is the accelerating force that I am providing, because of which accelerating force the car is moving, the velocity of the car is changing. So the output of the system is the car velocity, and the position of the car means that is the displacement of the car from a fixed reference point. So what we want from this model is that we want to develop a simple model to control the velocity of the car. So we need to find a model, as in we need to find the relationship between the velocity of the car with the force which is being applied, which is F. Okay, so for that the first step is the purpose of the model. So the purpose of the model is that we want to understand what is the velocity behavior of the car, how the velocity of the car is changing with the input accelerating force. Okay, so then we'll define the boundaries. So the boundaries is the car is the system that we need to control, and the surrounding environment is that the highway or the road on which the car is traveling, that will form a part of the environment in which the system is acting. Now, if you want to see the mechanism or understand the mechanism of how this velocity is being generated because of this force, so that means you see that from the mechanical structure of the car, you can see that the thermal energy is converted into kinetic energy. Thermal energy as in because of the because you are applying an accelerating force, so because of that there is more fuel is going into the engine, and then there will be fuel is burnt, so that means there is some thermal or heat energy which is generated, and because of that heat energy that is getting converted into kinetic energy, because of which the car is moving and you are getting a change in the velocity of the car. So now let us say that the mass of the car is m, and since the car is moving on the road, and the road obviously is not a frictionless road, so that means there will be some kind of friction between the wheels of the car and the highway, and that friction will be acting in the opposite direction of the movement of the car. Okay, so that means you can represent the car with a mass with a mass m, and the frictional losses that can be represented as a damper, so that can be represented by B. And let us say for now, because of like simplicity purpose, we will ignore all the other losses in the car, like the thermal losses or the rotational inertia of the wheels. Those things are ignored as of now in order to make make a simplistic model. So now the variables of interest is that the displacement, which let us say we have because of that accelerating force, the car is getting displaced by a amount of x, and that the velocity of the car is v, which is equals to nothing but dx by dt. And everything is happening because there is an accelerating force F. So F is my input, x or v, you can say that either v is your final output, because we want to see the cruise control, so that means we are more interested in the velocity of the car rather than the displacement of the car. So now if you model this car, so you can say that the car is modeled as a mass m, and the friction between the car and the surface on which it is moving, that is modeled as a damper with B. So now let us say that the direction or of the displacement of the car is in the positive. So this is, let's say, 0 position, and this is the positive position. So that means the inertia or the accelerating force, you can write that accelerating force will be equals to m into, if x is the displacement, so m into x double dot, and the frictional force which will be acting in the opposite direction will be equals to b into x dot. Now now how are these two factors interlinked? So we'll see that, so the overall accelerating force, that will be equals to the applied force minus the frictional force. So let us say that accelerating force is Fa, so that Fa is equals to mx double dot, and the applied force is F, and the frictional force is F of F. So you can write that the applied force minus the frictional force will be equal to the accelerating force. Now if you substitute the values of this frictional force and accelerating force, you can see that the equation will look like F minus Bx dot equals to mx double dot. Now x dot is nothing but velocity, and x double dot will be equals to the acceleration, which is equals to so x double dot is the acceleration, which you can write is equals to the derivative of the velocity. So now from this equation, you can find the final mathematical model. So you can write F minus B into V will be equals to M into V dot. And then from there, you can write the final mathematical model is V dot plus B by M into V equals to F by M. So this is the differential equation model of a car which is moving at a velocity of V because of application of some accelerating force of some external force F. Okay, so this much is clear?
Yes, ma'am.
Okay. So now let us see one more example. So let us take an example of a very simple pendulum. Okay, so a pendulum is what? Pendulum is nothing but there is a mass which is hanging by a string. Let us say that the length of the string is L, and it is hanging at a fixed position. There is a pivot, so there is a fixed reference, or there is a fixed plate from where a mass or a ball is of mass m is hanging, and the length of the this the length of the string is L. So this so what happens is that if you take so this the equilibrium position of this pendulum will be if it when it is lying here. So the pendulum is somewhere over, let's say, here. So now what you can do is that you can take this pendulum and move it to a specific angle theta. So let us say the angle theta between the equilibrium point and the point at which you're starting to release the pendulum, that is theta. So now if you take the pendulum to this point at an angle of theta and then you release the pendulum from here, so what it will do, it will oscillate back and forth. It will move all the way till here. So let us say this will be another angle theta. It will move all the way here. Then again in the next one, it will again move here and so on and so forth. It will keep on oscillating until and unless because of the external damping and all, it comes back to its original equilibrium position where theta is equals to 0. Okay, so ideally if you don't have any damping or anything, if you're performing this experiment in a vacuum, then if you release the pendulum from an angle of theta, it will keep on oscillating forever. So on the right side it will go on till angle theta, and on the left also it will go on for till an angle theta. But obviously in the real life that is not the case. So there will be some frictional force because of the environmental environment or the air. So because of that there will be a damped oscillation and it will keep on oscillating and it will come back to its original or rather the equilibrium position. So now the purpose of this model is that we need to study what is the motion of the pendulum. So what will be the system which is being considered? One is that there is this is the pivot. So this part is the pivot. Then you have this string and then you have the mass. So this forms the whole system. So the here what is happening is that there is energy transformation between kinetic energy, between potential energy and kinetic energy. Because when you are moving this pendulum to this point, so that means there is a change in the angle and there will be some potential energy stored. And the moment you release the pendulum from here, it will keep on oscillating. So that means whatever potential energy it had gained at this point, that will be converted into the kinetic energy. So we'll model two types of system with friction and without friction. So first, so the variable of interest here are the angular displacement, which is theta, and the angular velocity at which the pendulum would be moving when you release it from this point. Okay, so the elements will be, there will be a rotational torque, there will be frictional torque, there will be moment of inertia, there will be the angular velocity. So the rotational torque, if you want to model that, so rotational torque you can model by TR will be equals to J into theta double dot, and you can substitute J by ML square. So TR will be equals to ML square theta double dot. And the torque which is there because of the gravity, because this is mass, so mg is going downwards and there is another force which is acting in this direction, that is given by mg sine theta. So the torque which is happening because of this gravitational force, that is given by mg L sine theta. So now these two torques will be acting in a direction opposite to each other. So you can say that TR will be equals to minus TG, and then if you write the equation of these two over here, so then you can, the final differential equation model will come as theta double dot plus G by L sine theta will be equals to 0. So this is a sort of we are ignoring any kind of friction which is there. So this is a lossless kind of a system. If you consider a system where there is an additional or frictional loss which is given, which is present other than this gravitational force, so that means, so let us say that TF is the frictional torque, and you can write TF is equals to B into theta dot. So now if you again apply the physical laws, so you will see that the rotational torque because of which the pendulum is moving, that will be equal to the losses. So one is the frictional torque and the other one is because of this gravitational force. So you can write TR will be equals to minus TG plus minus TG minus TF, and similarly you can write the mathematical model. You can substitute these mathematical equations and finally you will get the mathematical differential equation mathematical model of a pendulum. So in this way, whenever you are given a system, so first of all what you need to do is that you need to figure out what is the aim of the modeling, what is the output that you want and how. So the main thing is that you need to find the relationship between the input and the output. So you need to consider all the factors which are affecting the output apart from the desired input that we are providing, the frictional losses, the external disturbances, what all are there, and you try to model each and every element. So if there is a frictional loss, you model that frictional loss in a separate way, and then finally combine everything together and then figure out what is the overall mathematical model of the system. So next we will move to something which is known as transfer function. So I will briefly touch upon transfer function because we will deal in more details later on. But you need to know a little bit about this transfer function because otherwise you won't be able to understand the next topic. So then a transfer function, or rather we have seen that when you have a control system. So a control system is what? You have an input, you have something here. So this is your input, let's say R, the output is C, and this is your system. So, and this system is basically, it has some, it is basically some functional, it is giving some kind of a mathematical or some functional changes to the input so that you get a output. Fine. So now we want to see what is the, so one way of representing the system was using the differential equation model, which we had seen till now. And the second way of representing a system or modeling a system was, if you remember, that it was based on a transfer function model. So in a transfer function model, what happens is that this system, so the definition of transfer function, so first of all, the transfer function, it can be applied only for a linear time invariant system. Okay, so if you have a linear time invariant LTI, linear time invariant system, then the transfer function is defined as the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable under the assumptions that all the initial conditions are 0. So now if you have this C as, or if I write, let's say, at par with this equation. So if you have Y as your output and X as your input, now if you take the Laplace transform of this output function and similarly you take the Laplace transform of the input function. So Ys by Xs will give the transfer function. So transfer function, so this will be represented by Gs. So the input will be Xs and the output will be Ys. So now what you can say that if xt and yt, these are like the time domain representation, and similarly the frequency domain representation will be xs and ys, then the ratio of ys by xs, the output and the input of a block or of this system will be given by, is known as the transfer function of the system. Now another definition of transfer function is that it is the Laplace transform of the impulse response of an LTI system. Why impulse response? Because if you say, if you write the equation for an impulse, so xt is equals to, let us say, an impulse function that is equals to delta t. Delta t or impulse means what? That at time t equals to 0, xt has a value of 1, and at all other value of t, the value of xt is equals to 0. And if you take the Laplace transform of an impulse function, it gives xs is equals to 1. So now you can say that if xs is equals to 1, then gs will be equals to ys. So we can write that if you have an impulse input, if you give an impulse input to a system, to a linear time invariant system, then the output of the system that is given by the transfer, that is equal to the transfer function of a system. So let us take an example, like we have seen that in a spring mass damper system. So in that spring mass damper system. So the differential equation model was given by F equals to, let's say it was mx double dot plus b x dot plus some k into x. So now if you take the Laplace transform of this whole equation, then we will get Fs will be equals to m into s square xs plus bs into xs plus k into xs. Then from here, if you write the if you take the output, so output is here xs by fs. Fs is my input, so gs will be equals to xs by fs, which will be nothing but 1 by m of s square plus b of s plus k. So this is the transfer function of a spring mass damper kind of a system. So this so from this transfer function you can see that it is dependent on the system parameters. So m, b, k, these are all the system parameters. So the transfer function is dependent on the system parameters only. It is independent of the type of input that you are providing. Since we are taking a ratio of the output to the input, so that means the transfer function will be independent of the kind of input that you are providing, but it only will depend on the system parameters. It will only depend on the parameters of the system. Now we'll see what a block diagram is. So a block diagram is basically, you can say that it is a pictorial representation of the functions which are being performed by each component of a control system, and it defines how the flow of the signal is happening through the system. So the overall block diagram, it basically depicts or it represents the interrelationships between the various components which are present in the system. So we have seen that in a control system you have your input, then you have, let us say you have a controller, then you have this is a controller C, then you have your plant E, and this is your output. And you can have feedback also like this, which is given by H. So this will be, so you are representing each element of the system. So controller is one element, plant is another element, this feedback sensor is another element. So you have different elements which combined together forms the overall system. So in all these systems, they are represented as one blocks. So these blocks, basically it is a functional block, and the mathematical operation of this functional block or the that is being performed. So whatever is there inside the block, the mathematical operation is performed on the input in order to produce the output. In general, when you are drawing, when we draw a block diagram, we generally use the transfer function is usually given as the input, or it is entered in the functional blocks, and the direction of the flow of the signal that is given by the arrows. So in a block, the flow of the signal is unidirectional. So there will be a direction, the input signal flow will be unidirectional. Similarly, the output signal flow will also be unidirectional. So this is like more or less the concept of block diagram. So this is, you can say that this is the block diagram of a closed loop system. So you have your input RS, then let us say that the forward path the plant that is given by the transfer function of that plant is given by GS, and the output that you are getting is CS. And similarly, you have a feedback path which is given by a transfer function of HS. Now what we want here is that we want to find the transfer function of the overall system. So GS is the transfer function of the system. You can say that this is for the forward path, and HS is the transfer function of the feedback path. So now if BS, so you can write that BS will be equals to CS multiple. So the input of this HS block is CS and the output is BS. So BS will be equal to nothing but CS into HS. Similarly, for this, the input of this block GS is ES and the output is C, and so you can write C will be equals to GS into ES. So now if you, and this error detector that is actually comparing the reference input RS and the signal Bs. So Es will be equals to nothing but Rs minus Bs. And why we are using this feedback? So just to recap, the role of the feedback is that it modifies
power will come.
Yes, ma'am.
Okay, so in case you have any doubts and all, I'll try to clear it up in the next class. So tomorrow we'll have class at the scheduled time. So at 11 o'clock we'll have our class. Okay.
Yes, ma'am.
Thank you, and sorry for sort of leaving you incomplete for not completing today's lecture. Continue it tomorrow.
Thank you, ma'am.
Okay, thank you. Bye.